Have you ever looked up at the night sky and felt a sense of connection? There's a profound reason for that. The iron in your blood, the calcium in your bones, the very oxygen you breathe. Every single atom was forged in the heart of a star that lived and died long before our Earth even existed. You, me, and everything on this planet are quite literally made of stardust. It's a poetic truth, backed by the grand story of cosmic creation. To understand the birth of our world, we must travel back in time. Our story begins not with a planet, but with a possibility, some 4.6 billion years ago. Long before there was a sun to warm us, or a planet to stand on, there was just the quiet, cold expanse of interstellar space. Imagine a colossal, dark, and frigid cloud of gas and dust, adrift in a spiral arm of our Milky Way galaxy. This wasn't just empty space, it was a molecular cloud, spanning light years across. It was a place of immense potential, a stellar nursery where new stars were waiting to be born. For millions of years, this cloud remained in a delicate equilibrium. The outward pressure of its sparse gas molecules perfectly balanced the gentle, persistent inward pull of its own gravity. It was a cosmic recipe, composed mostly of primordial hydrogen and helium from the Big Bang. But it was also sprinkled with a precious dusting of heavier elements: carbon, silicon, iron, all forged in the nuclear furnaces of previous generations of massive stars. These stellar ancestors ended their lives in spectacular explosions, seeding the galaxy with the raw materials for new worlds. Our solar nebula was a cosmic inheritance, waiting for a trigger. That trigger came from a dramatic, violent event. The shockwave from a nearby exploding star, a supernova, ripped through the nebula. This cosmic jolt was just enough to disrupt the cloud's fragile balance, pushing pockets of gas and dust closer together. With the balance broken, gravity seized control. The slightly denser regions began to pull in more and more material. A slow, inexorable collapse began. What was once a diffuse cloud started to coalesce toward a common center. As the cloud collapsed, it began to spin. And as it shrank, that spin accelerated dramatically, thanks to a principle called the conservation of angular momentum. It's the same reason a figure skater spins faster when they pull their arms in. The vast, sprawling cloud was now becoming a compact, rapidly rotating vortex. This spinning motion prevented everything from simply crashing into the center. Instead, the material flattened out into a vast, rotating disk, like dough being spun into a pizza base. This structure, known as a protoplanetary disk, is a common feature of star formation we now observe across the universe. At the very heart of this swirling disk, the gravitational collapse was most intense. The vast majority of the cloud's material, over 99%, was funneled into the center, forming a dense, hot ball of gas called a protostar. Here, the pressure and temperature soared to unimaginable extremes, reaching millions of degrees. Finally, a critical threshold was crossed. The core became so hot and dense that hydrogen atoms, the most basic building blocks of the universe, began to slam into each other with enough force to fuse together, forming helium. This process, nuclear fusion, unleashed a colossal amount of energy. With a brilliant, sustained flash of light and heat, our sun was born. A star ignited, and the solar system was bathed in light for the very first time. This newborn star was not alone. It was still surrounded by the spinning protoplanetary disk, a vast platter of leftover gas and dust that would soon give birth to all the planets, moons, and asteroids in our solar system, including our future home, Earth. The young sun's fierce radiation and powerful solar winds began to shape this disk, blowing the lighter gases like hydrogen and helium toward the outer reaches. Closer in, where the heat was more intense, only heavier, rocky, and metallic grains could survive. These durable particles were the fundamental seeds of the terrestrial worlds, the building blocks of a planet yet to come. In the vast, spinning disk of gas and dust surrounding our young sun, a new world was waiting to be born. It all began with the smallest of things, countless tiny dust grains, no bigger than particles of smoke. These weren't just inert specks of rock. They were a complex mix of silicates, carbon compounds, and frozen water ice, all swirling together in a cosmic dance. In this cold, diffuse environment, the first force to bring them together was surprisingly familiar. At first, static electricity made them clump, like a balloon sticking to your hair after you rub it. Gentle collisions weren't destructive. Instead, these charged particles clung to one another, forming fluffy, fragile aggregates. Through millions of these gentle encounters, little specks became bigger specks, then pebbles. This process, known as accretion, was slow and patient. Over thousands of years, these fluffy dust bunnies compacted into solid objects, centimeters to meters across, creating a disk now filled with a swarm of primordial pebbles. As these clumps grew, a new force began to take over. Their own gravity, once negligible, started to matter. It began to pull in more material from the surrounding disk. This gravitational focusing was a tipping point. The bigger an object got, the more efficiently it could sweep up its neighbors. Like a snowball rolling downhill, they gathered more and more mass. Pebbles became boulders. Boulders crashed together to form objects the size of mountains. The solar system was becoming a more violent place. These growing bodies were on cosmic collision courses, bumping, smashing, and sometimes merging. Over millions of years, this relentless process of collision and merger built larger and larger objects. Eventually, objects hundreds of kilometers across formed. These were the building blocks of planets, the planetesimals. Space was chaotic, crowded, and messy, a demolition derby of rock and metal where only the strong and the lucky survived. Each impact added mass, making the survivors larger and gravitationally more dominant. The biggest of these were now protoplanets, planetary embryos on their way to becoming true worlds. But these collisions did more than just add size. They delivered immense energy. This, combined with heat from the decay of radioactive elements trapped within, caused temperatures to soar until the entire protoplanet began to melt. Early Earth became a giant ball of molten rock, a glowing magma ocean thousands of kilometers deep. In this planetary crucible, a crucial process called differentiation began. The heaviest elements, primarily iron and nickel, were no longer supported by solid rock. Pulled by gravity, they began a catastrophic plunge toward the center. This iron catastrophe formed Earth's dense metallic core. Meanwhile, the lighter silicate materials floated upward, eventually cooling to form the thick, rocky mantle and the planet's first fragile crust. This fundamental layering wasn't just about structure. The churning liquid iron in the outer core established a powerful dynamo, generating the magnetic field that would one day shield our world. And the heat trapped within would drive volcanic activity for billions of years to come. For tens of millions of years, this violent bombardment continued. With each collision, Earth cleared its orbit, asserted its gravitational dominance, and settled into the spherical shape we know today. A planet was built. Just when early Earth had endured so much, a cataclysm arrived. About 4.5 billion years ago, Earth, still mostly molten, was not alone. A Mars-sized body, Theia, was on a collision course. Theia didn't graze Earth, it slammed into it with unimaginable force. The impact vaporized vast amounts of rock, blasting debris far into space. Much of that debris didn't escape. Earth's gravity captured it as a hot ring. Theia's core likely merged with Earth's, boosting our mass and density. Over time, orbital debris clumped, gravity pulling pieces together. Eventually, one large sphere formed, the Moon. This is the giant impact hypothesis, the leading explanation for the Moon's origin. It explains the Moon's mantle-like makeup and its relatively small iron core. The Moon's gravity braked Earth's rapid spin from 5-6 hours per day to 24. It also stabilized Earth's axial tilt, preventing wild wobbling. Predictable seasons followed, a key condition for complex life to evolve. The moon isn't just a pretty light, it's our planet's essential anchor. Our young planet was forged in fire and steam, a world still reeling from its violent birth. During the Hadean Eon, Earth was a hellish global magma ocean. There were no continents, no oceans, and certainly no life. The surface, kept molten by leftover heat from its formation and constant bombardment from space, was a roiling, incandescent sea of rock. As the planet slowly began to cool, volcanoes furiously pierced the thin, primitive crust. They spewed immense quantities of gas, steam, carbon dioxide, nitrogen, and traces of methane and ammonia, a process called outgassing. This primordial atmosphere was thick, toxic, and contained virtually no free oxygen. A thick, planet-wide blanket of steam trapped the immense heat radiating from the surface, creating an intense greenhouse effect that kept temperatures scorching for millions of years. Then, as the surface finally cooled below the boiling point of water, the rains came. The superheated steam in the atmosphere condensed and began to fall, not as a gentle shower, but as a relentless, planet-altering deluge. It may have rained continuously for millions of years. This colossal storm filled the vast basins and impact craters carved into the young crust, slowly forming the first oceans. While much of this water came from volcanic steam, a significant portion was delivered from space. This late veneer of icy comets and water-rich asteroids bombarded Earth, contributing their frozen cargo to the growing global sea. These primordial waters were far from the blue oceans we know today. They were likely hot, acidic, and thanks to vast quantities of dissolved iron, an eerie shade of green. This was the birth of the hydrosphere. With oceans formed, the stage was set for the greatest mystery of all, the origin of life. In these chemical-rich waters, simple organic molecules began to form and interact. Did life begin in the sun-drenched shallows of tidal pools? Or did it spark into existence in the dark, energy-rich environment of deep-sea hydrothermal vents? Scientists are still working to find the answer. But somehow, around 4 billion years ago, these simple molecules organized into complex structures, enclosed themselves in membranes, and developed the astonishing ability to replicate. The first cells were born. Life had begun. For billions of years, life remained simple. The planet was ruled by microscopic organisms like bacteria and archaea. They were tiny, but their collective impact would be nothing short of planet-shaping. A revolutionary group called cyanobacteria evolved a new trick: photosynthesis. They harnessed the power of sunlight to turn carbon dioxide and water into food. As a waste product, they released a gas that would change the world forever: oxygen. For hundreds of millions of years, this new oxygen immediately reacted with the iron dissolved in the oceans, causing it to precipitate and settle on the seafloor. The oceans literally rusted. Once the iron was gone, oxygen finally began to build up in the atmosphere, triggering the Great Oxidation Event. Meanwhile, the planet's surface was also in motion. The cooling crust had thickened and broken into massive tectonic plates. These plates began drifting, colliding, and sliding beneath one another, recycling rock and chemicals. This geological engine created a crucial feedback loop, helping to regulate the global climate over eons and making Earth a more stable home for life.